Hello and welcome to Stars, Cells, and God. My name is Jeff Zweerink and I'm joined today with Dr. Hugh Ross, and we're going to be talking about emotionally intelligent AIs and dark matter. Well, Hugh, it's good to have you here on the show today. I'm just going to throw it open to you because you're going to be talking about dark matter, dark photons, and cosmology. So what do you have for us today?
Well, these are two papers that got published recently. This one in Physical Review Letters got published last October and was astronomers looking at maps of the cosmic microwave background radiation, trying to determine if they could see a signal of what are called dark photons. And I say, how can photons be dark? Dark photons are light.
Seems a little oxymoronic.
It does. Well, this is some speculation by astrophysicists that in the early universe, it may have had the properties where you got a complement of photons, where you got photons that are dark.
Meaning what?
They're a particle,
Okay.
like a photon, but that they would have the property that they could actually convert into photons, which means you could see them. And likewise, they're saying there's a possibility that photons could become dark. So think of it as a light switch. The light comes on, the light goes off. So two different kinds of particles that have the capability of, so it'd be kind of like an electron and an anti-electron. So
Okay. So these are photons in a very real sense. They just are not quite the same electromagnetically as the photons that we interact with.
So
Okay.
You would put it in the category of dark matter particles.
Right.
Okay, which means that they have the property that they either don't interact with light at all, or they're very weakly interact with light. And there's certain cosmological models that predict that you're going to get these dark photons coming out of the early universe. I mean early. I mean previous to 10 to the minus 35 seconds.
Right. Okay. So that's
really
way
close to
back
the
before
beginning of
grand
the
unified.
universe.
Yeah.
Right.
And so this is pretty exotic type of particle. I mean, these are, at least when you're talking about WIMPs, which are another dark matter particle, there you have this idea that, okay, we got bosons, we got fermions, and the symmetry in there would give more particles than what we can see. So this is kind of an extension of particles we see. This seems a little bit more exotic than that to me.
Yeah, and we're talking, these particles actually have mass, so that's why they think this would be part of the dark matter. There's about 6.5 times as much dark matter as there's ordinary matter.
Right.
So we've already found neutrinos as dark matter, but everybody realizes they make up a very tiny percentage of the total amount of dark matter that gravity tells us, or the gravitational dynamics of galaxies tell us must exist. So we know there's lots of this dark matter, but the only particles we've found so far are these neutrinos. And astrophysicists are really trying to say, hey, can we really find the rest of the particles that make up this dark matter? These dark photons are a candidate. And I say a candidate. Most astrophysicists that I've talked to about this would say, yeah, we think these particles might exist, but we don't think it makes up, say, 90% of the dark matter of the universe. So it's kind of like in the same category as these neutrinos. They're dark, but they don't explain the existence of all the dark matter that gravitational interactions we observe in the universe tell us must exist. But the reason for the interest, this was especially brought up in the paper published in October, where they looked at the cosmic microwave background radiation maps, as a number of cosmological models predict that this extremely early era of the universe will produce these dark photons. And when they convert into photons, we can see them, which means we can look for areas in the universe where we'd see more photons than we expect to see. And so we basically say, okay, we'll subtract off the photons we know are part of the normal universe. The excess photons could be a signal for these dark photons. So that's kind of what they're looking at. And I thought I would look at,
So was there some particular feature in the cosmic microwave background radiation that they're looking to explain? Or, I mean, my experience with this is that there's always a bunch of ideas of what they could be. Is this just, hey, this is a place we could go look for it, or were these particularly fascinating explanation for a feature that we see in like the cosmic microwave background radiation?
No, it was the other way around. They said, okay, let's actually look at the maps and see if we can see any signal of excess photons.
Okay.
So that's what they did.
Right.
It wasn't because they saw an unexplained feature in the cosmic microwave background maps. They said, okay, dark photons are being converted into photons. Maybe we can see this in the maps. And they wound up publishing a paper saying we couldn't see it. However, we established a rather firm lower limit on what they call, I think the technical term is, a dark photon mixing parameter, which is basically a technical term for the efficiency with which dark photons can convert into real photons.
So does this have the same flavor as neutrinos? And that's an ironic term now that I think about it, in that we know that there are, we can measure neutrinos, that there's a neutrino associated with the electron, a neutrino associated with the muon, a neutrino associated with the tauon, but these neutrinos can change from one to the other as long as they have some kind of mass. Is this motivated by that sort of, kind of that line of reasoning? That, okay, there's photons and there could be normal photons and other photons. Honestly, it just seems like a bizarre concept. Is this just something somebody came up mathematically that it works? Or I'm looking for a little bit of the background if you happen to know any.
Okay, well, there's a lot of different inflation models. In fact, I just read a book a few days ago on, these cosmological models, and I was rather surprised to discover there's over 1 million different inflation models, and they all predict different things. And several of those models predict that the inflation event, which happened about 10 to the minus 34 to 35 seconds ago, where the universe hyper-expanded at millions of times the velocity of light.
Well, at least it ended about that time.
Yeah.
So, yeah.
So that some of those models predict that you're going to have dark photons being produced. And so later in the universe, some of those dark photons could convert into photons. And so they said, well, the cosmic microwave background radiation, that's 380,000 years after the inflation event. Let's see if we can see it there. And they did come up with a fairly good limit that this dark photon mixing parameter was less than about 10 to the minus 8. So it meant that the efficiency with which dark photons can convert into photons is very, very low. And so...
Is that as straightforward as it happened, for every 10 to the 8 photons, one will convert into a dark photon and vice versa, or is that not so simple as that?
Yeah, it's as simple as that. And so they were able to say, well, the conversion efficiency is lower than this, which means it's going to be a little harder to detect. And this second paper was basically saying, we think we can get a better detection limit, maybe even see these dark photons. But I wanted to review quickly before I go into that. We talked about how different inflation models can predict this. As you're probably aware, what's happening in that first split second of the universe starts off extremely hot, which means you only have one force of physics. And that force of physics, as the universe expands and gets cooler, becomes 2, then 3, and then 4. And I think it was the Fermi particle accelerator that in the 1970s actually was able to prove experimentally that indeed, if you make the density of energy high enough, we can see electromagnetism and the weak nuclear force merging to become a single force. So this gave a lot of credibility to this unified field theory.
Right.
But a lot of unified field theories predict that you're going to get symmetry breaking when this one force becomes 2, then 3, then 4. And several of those models say that symmetry breaking will lead to the production of dark photons. So that's another way you can get dark photons.
Well, that's not just a interesting, maybe it is sort of exercise. That actually is the explanation for why photons have no mass and the W and Z bosons have a very large mass. And that's why that's why today the electromagnetic and the weak nuclear force look very different, is that the particles that mediate them have very different masses now. So this
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 fits.
naturally plays in with that sort of
Well,
idea.
what a lot of lay people don't realize is unified field theories actually tell us the universe begins with no photons. The photons show up at about 10 to the minus 36 seconds.
Okay.
And again, that's all part of the symmetry breaking. The final set of cosmological models that possibly could produce dark photons are these cosmic strings. And that's something they've been looking for in the cosmic microwave background maps, is that some people claim that as the universe goes through this unified separation, one force between 2, 3, then 4, you're going to get certain defects in the space-time continuum of the universe. Most astrophysicists don't believe there's going to be point defects, but a lot of them think there might be line defects, which they call cosmic strings.
Not to be confused with string theory at all.
No, it's different from string theory, exactly. So yeah, when you talk to a cosmologist, when he talks about strings, what kind of
You gotta be
strings are you
careful,
talking
yeah,
about?
make sure you understand that.
And these are basically defects in the space-time fabric, and that they can be straight lines, curved lines, they can be loops, they can be knots. And so there's a lot of different cosmic string models, and some of them predict you're going to get these dark photons. And so if we can detect these dark photons, that would tell us one of these models might be correct. And if we can get an accurate measurement, maybe we can say this is the one that's correct and these are not correct. Or if we can show that dark photons don't exist at all, that eliminates all those models from being possible explanations for the origin and history of the universe. So for cosmological reasons alone, it's
Right. No, I was just kind of thinking, okay, so it brings it down from 1 million down to what? 999. No, I'm curious how many of these I mean, is it a relatively small fraction that have these dark photons?
Yeah,
It seems like it would be, or I would have heard more about them. So,
well, I mean, as I mentioned, I just finished reading a 400-page book on all these different cosmological speculations of what's going on before 10 to the minus 35 seconds. And yes, you're right. Only a small fraction of all the models astrophysicists have come up with would be predicting you're going to get these dark photons.
right.
But eliminating that as a candidate would be a major advance.
Oh, agreed. Yeah.
Yeah.
No, I was being a
And
little snarky,
finding
but
them
it's cool. So.
would be an even bigger
Right.
advance. And so whether we find them or not, it's going to be a big deal, at least for astrophysical cosmologists.
Right.
So
So from an apologetic standpoint, what's the significance of this, and or what did you find interesting in this?
well, what I found interesting in this is that this all fits in. A lot of people who are not familiar with cosmological astrophysics look at some of these models as being a threat to the Christian faith. And, again, having read this 400-page book, it's like all of them are compatible with what the Bible teaches about the beginning of the universe. You just have to be careful to define what you mean by the beginning of the universe. So,
Yeah, that's an interesting point, because that's what I found when I started investigating the multiverse. Is like the multiverse, it seems like, oh, that's a threat to Christianity. And it can be, depending on what exactly kind of multiverse you're talking about. But in general, most research into the multiverse actually, I would argue, makes the cosmological and teleological arguments, beginning in a design argument, actually stronger. And so instead of needing this specific set of circumstances, it makes it a more robust argument. And it sounds like you're saying the same sort of things going
well,
on
I'm
here.
also saying I think this is going to have benefit for the fine-tuning argument. Whichever way this research goes, I think is going to uncover more evidence for what you see in Job and Psalms. And no matter where you look in nature, you're going to find evidence for the supernatural handiwork of God. The fine-tuning is ubiquitous. You and I have written books on this. At all cosmic size scales, we seem to uncover this evidence for fine-tuning.
So what part of the story at this point regarding dark photons would give you indication of that? It seems like we don't even know whether they exist, so how could they be evidence for fine-tuning?
Well, first of all, dark matter is a key component of the Big Bang creation model. And you got a few people still out there doubting this. And so again, we found neutrinos, so we know at least some kind of dark matter exists. Finding another candidate of dark matter particles that we can prove exists, I think would buttress our evidence for the biblically predicted cosmic creation model. If we could actually get some good measurements on whether or not this dark photons exist, I think that's going to lead us to discover, hey, here's additional fine tuning that we didn't even know. I mean, that's what's happened. Every time we've been able to push the frontiers where we get better measurements, we discover, oh, here's some fine tuning we didn't see before.
Right, yeah.
And so I'm saying for that reason alone, this is worth the attention of Christians. Let's just see where this goes. And no matter which way it goes, I think it's going to give additional evidence for the Christian faith.
You know, it strikes me as a couple of things that have come up to me. You know, we've had discussions on this show and other places about the galaxies early in the universe. And, you know, go back before James Webb was launched. And, you know, we've got measurements by Hubble. We've got the cosmic microwave background radiation. Given the cosmic microwave background radiation, we could find a pretty reasonable interpolation between the cosmic microwave background radiation and the galaxy we saw and said, yeah, this all works. Well, now that we're finding more complex galaxies than we thought in there, it just turns out that instead of that kind of simple extrapolation, it's a more complex picture, which initially looked like it was a problem for Big Bang cosmology. In reality, what it's showing is that it was a more complex picture, which I think ends up being the complexity actually allows that fine-tuning and design to show up. Because if it was simple, that's pretty straightforward. But if it's a very complex picture, that's often where the fine-tuning shows up. And so it seems like there's a parallel sort of scenario at play here.
And there's another parallel in the sense that, when the Big Bang was first proposed in 1925, a lot of astrophysicists who are not theists said, this looks too much like what the Bible talks about. We got to get rid of this. And so there was quite an attempt in the 20th century to replace the Big Bang. And what actually happened over the past 100 years, it's been 100 years now.
I know.
Yeah, is that, we began with this kind of Big Bang model. We didn't know whether it started off hot or cold. And then they said, okay, the new measurements show us it can't be cold. It's got to start off hot. It's got to start off very dense. And so we had this broad range of possible Big Bang models that suddenly became smaller. The cold Big Bang models got eliminated. But we still had a family of Big Bang models. But what's been happening with the past 100 years, it's always been a family of models, but the breadth of the models has become narrower and narrower and narrower. You just mentioned the James Webb. It's basically eliminated several of the Big Bang creation models that were viable, 5 years ago. But we still have a family.
But more detailed models.
They're more detailed models.
Big Bang model basically was, okay, the universe is expanding like this. Now we know it's expanding like this with dark matter. There's a whole lot more detail in it than it used to be. And I think that's really cool. So.
But my main point is the argument that you've got an accurate explanation or model for what you're observing is if you see the family of models clustering into a narrower and narrower confine. And often the layperson says, I really want to see it get down to one model. And the bottom line is no matter what scientific model you're looking at, that never happens. But you're
really
on the right
yeah.
track if the family of models becomes more and more compressed as you learn more and more. And I think that's where this has some potential. We can narrow the family of Big Bang creation models. And if we're successful in doing that, that gives us even more evidence that the Bible got it right thousands of years ago when it predicted these features of Big Bang cosmology. So these are the different cosmological models that are at stake. And these are the most recent papers published on trying to define these dark photons. What fascinated me about the paper published just a couple of weeks ago is they said, well, to really get a good view of these dark matter or these dark photons, assuming they exist, we need to be able to make measurements where we have a broad range of energy intensities. And what they were able to determine based on what was published in October, the best place, our best possible opportunity to see dark photons going into photons, and then we able to see the excess is plasmas. So, and when you look at the cosmic background radiation, you're looking at a plasma.
Right.
But they said, here's another plasma place we can go where we can see a broad range of plasma intensities. And that's basically the solar plasma.
Right.
And what's interesting about the solar plasma is it extends even beyond the orbit of the Earth. So
It's pretty not as dense out here. That's
no,
for
it's not
sure.
as dense out there. But a lot of people think, okay, the corona of the sun, that's just around the sun. And you and I have both been at the solar eclipses in 2017 and in 2024. What was wonderful about the 2017 eclipse, because it was such a short eclipse, you really got to see the corona way, way out.
Right.
So,
Well,
and
the weather was a little better. That helped a lot too.
weather
so-
was a little bit better, and because the eclipse was shorter, you get actually a better look at that corona. So, but what they did is they said, we're going to actually use the data from the Parker Solar Probe. And the interesting thing about the Parker Solar Probe, it's unlike any other probe of the sun in that they purposely put it on a highly elliptical orbit.
Okay.
So the orbit basically goes from the Earth all the way to about 10 times the radius of the sun. Or to put it in astronomical units, from about 0.04 astronomical units out to 1 astronomical unit,
Okay.
which means they get to survey a broad range of solar plasma density.
Right.
When you're really close to the sun, you're seeing very high plasma density. When you're around the Earth, as you just pointed out, it's pretty feeble. And then they can sample the entire range.
Right.
And that's Parker's.
Incidentally, what's its orbit period? Do you happen to know off the top of your head?
I don't know off
Don't
the
know,
top
okay.
of my head, but I do know that this probe has been around for over 10 years. And so
Yeah,
it's been
it's got to be something less than a year.
Yeah.
With 1 astronomical unit or less.
So we're
it's gotta be
probably
that, so-
looking at least 20 orbits
Right.
where they got data. And that's what they did. They said, we're going to look at the publicly available database of what's come from the Parker Solar Probe. And, there's been like 20 plus orbits. We should get a lot of data
right.
that's going to help us to put a very, either detect these dark photons or put a much, much better limit on the mass of these dark photons and also the efficiency with which they can convert from dark photons to photons. So that was their mission. And I was impressed that they put a limit. They didn't detect these dark photons,
Right.
but they put a limit that was 20,000 times better than the limit that the people place by looking at the maps of the cosmic microwave background radiation.
So 10 to the 12-ish,
Well, 10 to the minus 13.
minus 13.
So
Okay.
it was 10 to the minus 8
Right.
was a conversion efficiency that they found with the cosmic microwave background radiation. What they published was somewhere between 10 to the minus 13 and 10 to the minus 14.
Okay.
So to be conservative, I took 10 to the minus 13.
Right. Okay.
And that's about 20,000 times better than
Okay.
what they got from the cosmic microwave background radiation. Then they end their paper by saying, this is just an initial attempt. We can do much better. They didn't look at all the data from the Parker probe, but they basically took what they thought would be a good sample
Right.
and published initial paper. So bottom line, this paper puts their foot in the door saying, hey, this is our initial attempt. We're going to publish more. So they're going to pull more data from the Parker.
Gotcha.
And the Parker's continuing to orbit. So we're going to get better and better data because the longer time you got, the better limits you'll have. I think it's possible, looking at what they've written, that in the near future, we might be able to go down to 10 to the minus 15.
So what do you think? Your assessment of, do you think something like this is the dark matter? I realize this is just your intuition here, or your assessment. It's not a here's the answer, if you will. But do you think it's going to be a WIMP? Do you think it's be an axion? Do you think it's going to be something like dark photons combination of?
Well, they already have a pretty good idea of the mass range if these things really do exist. And I'm trying to remember exactly what, oh yeah, here's the mass range. 3 times 10 to the minus 10 to 8 times 10 to the minus 8 electron volts. And to put that in context, an electron, which is a very low mass particle, it's 511,000 electron volts.
Right.
So we're looking at
Well, I mean,
something.
even the neutrinos that we thought up until recently were massless are kind of probably on the order of a fraction of an electron volt. So that this is pretty small. So
Yeah. So yeah, this would be even less than neutrinos. And because neutrinos are extremely abundant, but because they're so have so little mass, even though they're great abundance, when you multiply it by its mass, it doesn't add up.
right.
And you got the same problem here
Yes.
with these dark photons. We already know the mass is actually less than a neutrino. So even if they're abundant, it's not going to make much difference to contributing to the amount of dark matter we know must exist in the universe.
So it might be a piece of it, but the dominant piece is still
The
remains
dominant
to be found
pieces
somewhere
are
else.
somewhere else. On the other hand, if we can find these particles, it would basically say, okay, this is going to give us some insight that these cosmological models are the way to go, or if we don't find them, not these models, but we need to be focusing on other models.
Right.
So it's like, there's probably, 3 dozen different cosmological models out there that are considered viable, which means testable. So if we can eliminate a few of those, that would be huge for the cosmological community. And if we can establish them, that'd even be bigger.
Right.
So that's kind of the real goal. On the other hand, I would argue if we can find these dark photons, that means we don't have just one candidate. We got 2 candidates.
Right.
We've got the neutrinos, we've got the dark photons. That's just a spell, because I think as you're aware, young Earth creationists basically claim we astronomers are fooling ourselves in thinking there's any dark matter. And as we point out the neutrinos, they say, well, that's just a drop in the bucket. But if we come up with a second candidate, it's going to make it a little more challenging for them to just say, hey, these astronomers are just fooling us. So
Yeah, I have to say, I've always found that a little bit odd, that argument that, oh, we're just making up the dark matter stuff, because even if it's not dark matter, the alternative is something where general relativity is not right. I mean, the physics of that is really cool, and it still doesn't get by that it does a really good explanation for the universe we live in, and that we live in a Big Bang universe. None of that really fundamentally changes that. So,
yeah, I've been mystified by the same thing, Jeff, is that, why are young Earth creationists focused on dark matter? Because, if they're claiming we're all wrong about dark matter, the alternatives still leave you with an old universe.
it really does.
So, okay.
But no, I appreciate that. So I'm going to shift gears a little bit here, and I ran across an article about artificial intelligence. I've been just kind of watching and monitoring and seeing what's going on there. But in particular, this one is a paper that was published in Communication and Psychology. It was large language models are proficient in solving and creating emotional intelligence tests. And my particular interest in this, or why I think this is a relevant thing to pay attention to, is because, you've got AIs that can play chess. You've got AI. I mean, the spectrum of what AIs have gotten more proficient than humans is quite remarkable. And even games that or even things that require interactions with.
Couldn't hold that back.
That's all right.
Sorry. Go ahead.
Even things that require interactions and subtleties and deception, AIs have gotten good at that. And one of the things that I find really interesting is it's this confluence of what I think people perceive AIs as kind of these objective, rational, uninfluenced by biases, that they're, that's just that perception of AIs is like if an AI says it, then it's right and correct and it's trustworthy, it's rational. It's kind of the ultimate Mr. Spock, if you will.
Mm-hmm.
And yet as humans, we've got these emotions that we interact, and specifically how that plays out is that God has designed us to be relational, that we are because we're in his image, we are created in his image, we are inherently relational. And so we look for and relate. And we tend to anthropomorphize things. We look at this and say, oh, isn't the dog cute? He's thinking about, or oh, this. We give them human characteristics, and we're just kind of designed to do that because that allows people to interact well and have deeper relationships. And so this idea of AIs and emotional intelligence are kind of the confluence of these two things here, where and I think the titles are just kind of interesting. Could AI understand emotions better than we do? Generative AI can outperform humans in emotional intelligence tests. And then you go down and read through these AIs outperformed average human performance and were even able to generate new tests in record time. And the two that I thought were particularly interesting, in the end, from the authors, in the end, the large language models achieve significantly higher scores, 82% correct answers versus 56 for humans. This suggests that AIs not only understand emotions, but also grasp what it means to behave with emotional intelligence. This reinforces the idea that these LLMs, such as ChatGPT, have emotional knowledge and can reason about emotions. And I just think that's I think that's important to explore because the advances are really phenomenal. I think what they're doing with AIs is really cool, and the uses for these AIs are pretty remarkable. I have friends who have a son who's autistic. You're on the spectrum. That there are just so many things where if you can have AIs that can diagnose and be part of the diagnosis, read cues, get information out that humans either miss or because they're tired they might miss, or can actually just do it better. There are just so many features where these AIs can be used to help us take care of people better. And so being able to recognize some of those emotional cues and extract them to be able to I hesitate to use the word understand, but to be able to flag what the situation is, to be able to point out, here are the emotional things that are going on, here's how that plays out. Having AIs be involved in that would allow us to get better knowledge, better understand people so that we can take care of them better. And I think that's just a great thing to be pursuing. I say that with this hesitation because I have this suspicion that we're also going to substitute the quote-unquote emotional intelligence of the AI as though it were human emotional intelligence. And we're going to, instead of using AIs just for helping us understand and treat people better, we're going to use them as substitutes for human interaction. Because I could imagine an AI that seems to be able to interact in an emotionally intelligent way better than humans. Why not have the human interact with the AI instead of being able to interact with the actual person, if you will? Because a person is limited in time, limited in energy, limited in resources, gets tired, whereas the AI never does any of those things. And so I could see where we're going to substitute the human relationships, which is what we're designed for. We're going to have the AIs do that. And you don't get one without the other, so we need to be cognizant of that. And what I just kind of as a background, what they did was they actually looked at 6 different AIs. There's ChatGPT 4, ChatGPT 0.1, Gemini 1.5 Flash, Copilot 365, Claude 3.5, Haiku, and DeepSeek v3. Just a whole bunch of names of different AIs that are developed. And what they did is they ran them through a battery of tests that are these standard emotional intelligence tests to see how well the AI did. And at some level, I kind of reading some of the prompts, and these are relatively simple things. Like a guy at work had his idea stolen, and the credit was given to another person. And the other person was congratulated for it. What's the best response for this person? Is it to try and steal an idea back? Is it to try and be resentful of the colleague? Is it to talk to his boss? So there are some of these that are kind of simplistic, I guess I'll put it that way. They didn't seem like they were they weren't reflective of the actual real world scenarios where you play in it. But what I think is fascinating is that these AIs actually did better on these tests than most humans did. Because like I said, the AIs got the right response roughly 80% of the time, just over 80%, whereas humans will get the right response about 55% of the time. That's a
Well,
pretty large gap. So
yeah, but it's not a gap I wouldn't expect
why
because
so? I mean, agreed, but
because you're basically feeding in way more data into the AI system than most humans have assimilated. And so, for example, doctors now use AI to do diagnostics
right.
because you can feed data into the AI system that gives them examples of diagnostics far broader than what's available to most doctors. However, the doctors I go to, they always review the AI outcome because they're recognizing AI is going to miss things that the human will spot. And so it's important that a real doctor be the one
Oh,
evaluating
absolutely.
what's coming out. Now, my younger son's a clinical neuropsychologist, and they're actually developing AI systems to help the diagnostics at this kind of a level,
Right.
psychological and emotional. And, whereas doctors typically will talk to you for maybe 2 to 5 minutes and try to come up with a diagnostic. What I find interesting, just talking to my son, it's like 1 to 3 hours because they know they're dealing with the brain, they're dealing with people's emotional responses. It's going to take longer, but you can feed literally tens of thousands of diagnostics done by clinical neuropsychologists all over the world into an AI system, and therefore you put a human being down with the AI system, it's likely going to score better than most neuroclinical psychologists out there. It's still important.
No. Oh no, absolutely.
Yeah. So it will outperform because it's analyzing a far larger database than the human typically is able to analyze. However, it's still
Right.
important for the neuropsychologist who's a human being to look at the outcome and recognize, okay, I understand the biases that are built into the AI system. I know what data's been fed into it. I know what to look for to evaluate the outcome so I can help the patient. However,
That's
it saves
an
them
interesting point. I want to
yeah.
come back to that. Go ahead and finish your thought.
But the bottom line is it saves people like my son a ton of time.
No, and that's, I think that's one of the things I would advocate here is like, how do we use these as tools to help us do what we're doing without replacing the relational part of this that we're designed to do? Because I'm hard pressed to think that for very many instances, the actual physical interaction with another person is an integral part of the healing, especially when you're dealing with emotional stuff like this. And,
Well, you also mentioned, Jeff, that there's this tendency on the patient to prefer the AI system to the one who's the human being. And I think this is where the Christian perspective comes in. The human is a sinner. The AI system is just kind of spitting out data. So I can understand why in some cases people would say, I want the AI because it's not going to have those human feelings involved in it, hopefully.
Well, but I do think what you can get out of the AI is you can get, okay, so I'm a doctor or I'm any sort of surgeon, and granted, I have training and whatever, but at the end of the day, I am human. I'm going to be tired. I'm going to be wrestling with a relationship I have, irritable. Those things are going to influence me, whereas they won't influence an AI.
Right.
What I think we miss is that there are other things going on with the AI that are very different, and this is that intersection where we're inclined to anthropomorphize or see human features in stuff that are not human, because that person who's sitting there saying, I'd rather interact with the AI, has thoughts and is likely thinking the AI is doing something that it's not.
Right.
And just a couple of things, to wrap up what the study was able to do. They also went and looked and showed that these the AIs, the generative AIs, can actually produce these emotional intelligence tests very rapidly, things that take humans a long time to develop. And so it really does. There's something going on in the pattern recognition there that the AIs are able to see and perceive patterns and interact and mix with this. Now, one thing I do think that I find that raised a red flag for me, the fact that this was so much better than humans here, that humans were about 56, this was up at 81, 82%. It was reminiscent for me of what I was reading about a few years ago, Blake Lemoine, I want to say he was working for Google. I don't want to overstate, but I know he was working on a large language model. It was called Lambda. I'm almost positive it was Google, where he actually became convinced that this Lambda was sentient. And I remember reading through the transcript of Lemoine's interaction with the AI. And, there were some things where it's like it was multiple interactions and it was characterized as a single conversation. But what struck me about the response from the AI is that if you're looking and saying, okay, what are the features of a sentient being? The AI met every one of those exactly as you would expect, which no human would ever do. Because it's like the AI was giving the answers that it knew was expected. I hesitate, again, I still use this language. It's like the AI is thinking. It's not. It knows this set of input wants this set of output. That's what it's doing in there. That, whereas you and I are interacting here and talking, I'm saying words, you're hearing my words, you're generating thoughts, you're putting thoughts back into words. When we do that, we're doing something very different than the AIs. It was really just pattern recognition and a bunch of ones and zeros. And I remember two different AI scenarios that I've kept in the back of my mind as I'm interacting with what's going on in the AIs and how do we think about them. Is that one, an AI was trained to play Breakout. I don't know if you ever played that game. It's got a paddle that moves across the bottom, a ball comes in, and you try and get the ball up at the top because that it realized that when you play it, you can try and knock out every brick, or if you can get the ball up to the top, it'll knock out a whole bunch of bricks. That's the strategy to play. Well, the AI figured out how to play that, and it would bounce the ball up there. Now, we're doing that visually, so we're processing and figuring out, oh, if I get it, it's going to bounce around and do that. Well, the AI, it didn't even need to see a screen. You could just feed it in the ones and zeros, and it came up with that strategy. It's doing it very differently than we are. It's not saying, oh, this is the optimal way because the physics says this is the way it works. It's doing it because it's a pattern recognition is all it's doing there. And why that's important, and it plays out in stuff like this, is there was another study where a team of researchers were trying to assess how much people trusted an AI model. And this particular model was a classifier that looked at how to classify dogs and wolves, particularly wolves and Eskimo dogs. So, kind of similar looking creatures.
Yeah.
And they intentionally trained the AI so that it would classify dogs. The dogs were looked at 10 of them, and it got 8 of them right. One of the huskies was classified as a dog. One of the dogs was classified as a husky. But they trained the AI specifically so that it was actually looking for the snow in the background. And the ones that it missed were the ones where the dog had the snow and the husky didn't. But what was interesting about that is they looked at how many people trusted the AI. Well, about a third of them actually just trusted it because of how good how well the classifier did on predictions there. But once the AI, or once it was revealed, they found out a way to extract the reasoning, quote unquote, reasoning behind the AI. And once the explanation was given, the trust in the AI went way down. In these models, the paper itself actually articulated this. So there were at least 3 limitations to this. One is that the emotional intelligence tests are somewhat contrived compared to actual human interactions because there's a right answer and wrong answers. They're fairly straightforward. They don't have the subtleties of when I'm talking, I may be saying one thing and actually thinking something else, or just all sorts of the actual what we do as humans interacting is far more complex, and the emotional intelligence tests just don't have all that. They also recognize that there's a limitation in that the right and wrong emotional answers vary by culture. So these were all trained in a Western culture. And then also they noted that the black box nature of LLMs, these large language models, you don't actually know why it's doing what it's doing. And what I found interesting when the paper concluded, it said, hey, even though this is not as sophisticated as real world models and it's Western culture, these still show signs of actually being able to adjust the emotional, or to actually detect and interact with emotional reasoning. But I actually think that analysis of what's going on behind is probably the most important thing we need to be asking. Before I trust a large language model like ChatGPT or Gemini or all these other ones that are out there, before I trust them in what they're doing, ask the question, what are they doing? And at some level, that's a question of what's the model doing, and it's the worldview of the people who are designing it and building it, because that's going to go into the training and what's right. So it's not this objective Mr. Spock, all objective data type thing. There's stuff built into that that's AI, that's worldview, it's what's right, what's wrong. There's cultural norms that are built into there. And unless I understand that, I mean, I do that when I'm interacting with people. Where are you coming from? Where are you a skeptic or are you a Christian? Are you more artsy or are you more scientific? All of those help me understand how to, even without stereotyping, they help me understand what you're saying so that I know how to use it well. But it seems like if we're not careful, I think we may be inclined to not apply that sort of discernment in looking at the AIs.
No, I've always thought the best advice when people say, what do you think about AI, is always determine what data has been fed into the AI system first.
Right.
And so like with this system here, okay, what kind of data did they feed into the system? What samples of, emotional intelligence they feed into it? If I know that, then I know what I can trust from the system and what I can't trust.
So how would you respond? And I think this is accurate, but I'm somewhat guessing here, is that I know as I was doing studies on ChatGPT, pretty much that's like Wikipedia articles, there's just a bunch of stuff on the web that's being used and it's kind of uncurated at some level and it's all trained on that. And then now it's just that, and it's applied to these emotional intelligence tests. So they're not really trained on the emotional intelligence test. They're just
They're analyzing.
They're analyzing the test.
Yeah. AI is very good at analysis, not so good at reason. And so,
why do you say that? I'm curious. So.
Well, I mean, in the sense that you can give it a huge database or multiple databases, it can analyze it far more comprehensively and certainly much, much faster than a human can do. And so that's the value of an AI system. It basically speeds things up enormously. And that's what AI has been doing literally for the past 40 years.
Right.
It's been saving time for the human, but it's best used by the human who has the greatest expertise in what's being fed into the AI system. And so, but even if you're not an expert, just knowing, for example, with ChatGPT, you mentioned, it's basically been given the database of almost everything that's on the internet. So you need to recognize it's going to give you the common denominator from the vast amount of data that's on the internet. Now, what I like about ChatGPT is it tries to structure its answer for the user. So it actually gets to know me as a user and ask me questions.
Well, I will say, be careful about saying get to know you. I think it's doing something different than me getting to know you.
Well, it is. But what it does is, it will, give me, I'll tell it, look, this is my query. It'll feed it back in a few minutes, but then it'll ask me a question. How well were you satisfied with what I did?
Yeah.
And I say, hey, this was way off.
Yes.
Notice that goes into the database. That
Correct,
becomes part
Right,
of the data that it feeds. So every time I engage it, it gets to, quote, know a little better what I'm looking for and how to analyze the huge data it's looking at. And so I basically try to help it along because I want it to help me better. And I say, this is not what I'm looking for. This is what I'm looking for. And so it actually gives me an answer faster because it's looking at a smaller part of the database, and it's able to avoid certain biases. But it's because the human is actually helping it with this enormous database.
Well, and that's one thing I've often wondered. It seems to me that most of these chatbots, one of the designs or features around them is to get you to interact with them. I mean, that's what we do with social media, it's not really designed to give you information. It's designed to keep you on the platform, if you will. And I suspect most of the chatbots have a flavor of that inherent in the way they act. So of the people who I most appreciate are the ones who will tell me stuff I don't want to hear.
Yeah.
Keeping you interacting and telling you stuff you don't want to hear are a little bit at cross odds with one another.
They are, right.
And so I've wondered how much of what comes back is, hey, here's the best, most accurate answer, or here's what I can tell you that you're going to keep engaging on the platform. What's the actual algorithm driving the response in there? Is it really to get the best answer, or is it to get the best answer? The best response is the one that keeps engagement flowing.
Well, again, with ChatGPT, there are times where you need to tell the ChatGPT system, don't tell me what you think I want to hear. I want you to analyze this.
Well, but that requires an emotional intelligence on your part that you may or no. I get what you're saying. Yes.
Well, that's the whole point.
But the better we are at using the tool, the more likely it will give us good information. If we don't use it if we treat it like a person instead of a tool, we're likely to get a bad answer out of it.
We are, and it's also important not only to know what data has been fed into the AI system, what data has not been fed into the AI system.
No, I think that's important, yeah.
So especially for us scientists, we need to realize ChatGPT, it's not really surveying the whole breadth of the published peer-reviewed literature. It may in the future. And so we need to realize, okay, if that's what I want, forget ChatGPT. I'm going to go to PubMed. I'm going to go to the NASA ADS website and basically start going through all the published peer-reviewed literature. I do believe that things like PubMed and NASA ADS or Harvard site could be much enhanced with AI.
I think so. And
basically, it's already an AI system.
Yeah. But and that's where I think if you listen to me too much, it's like, oh, he's down on AI. AI is bad. I think more what I'm concerned about is, are we going to use it well?
Yeah.
And I think if we have as much as I've tried to think otherwise, my default, when I hear AI, I tend to think of, like you said, the Mr. Spock. It's the objective, always give the best rational answer, no bias. And we just have to realize, at least the state of AI today, it's always predicated on how it's trained, the biases that are in the data of what's being trained, the biases on the people who've designed the algorithms that decide what's good and bad. All of that's in there. If we recognize that, then we can use it as a tool and recognize its limitations, and we can use it well. And if we don't, we may be inclined to, especially the more it's able to mimic human behavior like emotional responses, we can avoid being caught up in thinking, oh, it's doing what I'm doing. We recognize, no, it's doing what an AI, the computer program, is doing, and we can use it appropriately.
Well, Jeff, you've often pointed out that people fear that AI is going to replace us. And the bottom line is that history of the past 60 years, AI doesn't replace me, but it sure makes me a whole lot more efficient. And AI is going to continue to do that. It's going to save me time. It's going to make me more productive. It's not going to replace me.
That is correct, presuming that we maintain the responsibility, or we maintain the maturity to use it well.
Yes.
I'm not really worried about the AI. I'm worried about how, as a people, we'll use the AI. And so I wholeheartedly agree with your
statement.
statement.
It's already being abused, no doubt about that.
Well, that's just the way life works. But I think there's I want to, if I can educate people and help them be aware so that they can use it better, that's just, I'm pleased with that. So, well, hey, thank you for joining us today. I want to encourage you to check out the discussion below and enter your discussion in the comments down there. Remember to like this video, subscribe for more content. We release new episodes of Star Cells and God each Wednesday here on YouTube and on your favorite podcast app. Be sure to share this video with a friend. Maybe have a good conversation about it. And remember, the more we know about science, the more reasons we have to believe in the God of the Bible.